This is an air pump, and so is this, and this. Although they look pretty different, the underlying physics for how they actually work is pretty much the same. Today, we're explaining how a manual air pump such as this actually work in order to help future us make our own pump, which will help fuel a rocket that we're also going to make later down the line. See, what you're watching right now is the first part of a mini-series on making our very own water-powered rocket. To power this rocket, we're going to pressurize water with air. And to do that pressurizing, we're going to make an air pump out of something I bet you weren't expecting. Anyways, to make that air pump by ourselves, we're going to need to know the actual physics of how any air pump works. So let's get right into it. To make this pump, we first need to know the actual parts we need to design. Your average bicycle pump has a few essential components. First, there's a pump barrel that all the other components are attached to. This is pretty much the body of your mechanism. For the pump I'm making, I intend to reinforce one of these pirouette cookie cans and drill holes into it to fit all the other components in. Even though the metal is pretty thin, like you can see when I press on it that it kind of bends. Can't really see it, but I have to reinforce it. I thought it'd be a pretty resourceful and kind of fun way to make the barrel for a pump. We have so many of these in the garage, it's actually insane. I think I'm gonna make the rocket body with one of these, probably gonna weld them together. Inside of this barrel, there's a piston. This piston has an inlet valve that opens when the piston is getting pulled up. When the piston is getting pushed down during compression, that inlet valve closes. To close off the pump, we need a lid that has a couple holes, right? One of the holes is so the piston can actually fit inside, and a bunch of the other holes are just to allow external air to come inside the pump chamber. These holes let the pump breathe between the air above the piston and the external air, right? So when the inlet valve opens, that air from outside can come inside the piston chamber and maintain atmospheric pressure. Instead of 3D printing it, I'm going to use the same lid from that can we talked about before, just to save materials and out of convenience, because these already form a pretty tight seal. Sorry. I'm just going to drill a couple holes in it, the big one for the piston, and a couple more holes to allow external air in. Next, a piston handle ergonomically simplifies the pushing and pulling action. We're considering it separately from the actual piston because it makes everything so much easier to print, right? It's not as awkward as a shape to print, because if you printed a piston with the handle, you need a bunch of supports coming out. So I'm just going to print the piston body and separately print out the handle and just attach it. Finally, we have an outlet mechanism that consists of a one-way valve that will allow air to go outside of the pump but not back in, as well as a modifiable adapter that lets you screw on the pump to basically anything, like a balloon, a water bottle, or even the upcoming rocket's propellant tank. You'll see what I mean in a future video. After all the parts are assembled, the pump works with two primary actions. Pulling up, called expansion, and pushing down, called compression. Pulling the piston up causes the air's volume to increase, effectively decreasing the pressure according to Boyle's law. As volume increases, pressure decreases due to air molecules having more room. However, our inlet valve prevents this pressure from decreasing, right? So when pressure is trying to decrease, that makes the ambient air pressure relatively higher than the pressure inside the piston chamber, right? This makes air pressure outside the piston chamber to want to come in, and our inlet valve only opens in this direction, right? So air pressure comes in, and the decreased pressure, which decreased momentarily, is almost immediately offset by the air pressure coming inside the piston chamber. This makes the air inside the piston stay at atmospheric pressure. Moreover, you may be thinking, it's a low pressure zone and there's also an outlet. Why doesn't it just come in through that? Well, it's called an outlet for a reason, right? It's also one directional. So when the relatively higher air pressure tries to rush in, that valve is forced shut, right? So air only moves in one direction, right? Straight into the piston chamber, straight out of it, right? There's no reversing. Now, when you push down on this piston, you're doing what's called compression, right? It decreases the volume inside the piston chamber which also according to Boyle's law increases the pressure, right? This is because as you decrease your volume, air molecules are packed tighter and tighter together and the pressure increases. This rising air pressure actually forces the inlet valve shut, right? But remember, when we were pulling it up, it would open to allow external air in. Well, now we have higher air pressure inside the piston chamber that wants to come out, right? It can't come out the inlet though, because in doing so, it forces it shut, right? It only opens this way. If you try to come out this way, it closes. Where does it go then? It goes out the outlet, correct? You have higher pressure inside the piston chamber and lower pressure inside the outlet. That higher air pressure is going to want to come out, right? So as we already said, it can't go through the inlet. So where does it go? It goes through the outlet, right? So because you have that higher air pressure, it's going to want to go this way, right? It already tried this way. It already tried every other way. It doesn't work. Only way it finds that it works is through the outlet, because the outlet opens up when air moves through it in this direction. But anyways, the higher air pressure inside the piston chamber will force the outlet valve to open up. If you try to go back in it, it will close. Again, the piston chamber remains at atmospheric pressure. Before, when it would decrease in pressure, that decrease would be offset by air molecules moving into it thanks to the inlet valve, right? Now we have the opposite. We have higher pressure due to our compression of the air inside the piston chamber, right? This is also offset thanks to the outlet valve. It opens up when it has higher pressure inside the piston chamber, so it goes back to atmospheric pressure, right? And whenever air tries to go back into the piston chamber, it can't because the outlet valve force shut. Anyways, it's important to note that when the inlet valve is open, the outlet valve is closed, right? This is open, air can come in. This is closed, air can't come through. It also works in the opposite direction. When this is closed, which occurs during compression, right, air can't go through, right, because you have higher air pressure inside the piston chamber. But the outlet valve is fully open, right? Air is coming right through it. So what I'm trying to say is two things. The pressure inside the piston chamber is almost always at atmospheric pressure, because whenever the pressure decreases, the inlet valve allows more air in, allowing stable air pressure. When the pressure increases, the outlet valve opens, allowing pressure to remain stable once again. And number two, with the inlet valve being open when the outlet valve is shut and vice versa, air only has one way to move, which is from expansion, in which air goes into the piston chamber, to compression, where the higher air pressure goes out into the outlet valve, right? It can't go in the opposite direction due to the unidirectionality of the valves. What this does is effectively transfer air pressure through the outlet valve into whatever we're trying to blow up, with air, not like actual explosives or anything. YouTube, please don't flag me. Moreover, the growing pressure inside whatever we're trying to blow up can't even go through the outlet valve, because that outlet valve only opens when there's higher air pressure inside the piston chamber, not the other way around. If it was the other way around, it would be forced shut. This may be a little tricky to wrap your head around, but please let me know in the comments if there's anything you didn't understand so I can help you comprehend it better. If you enjoyed the video and hopefully learned something from it, or you just like my sophisticated dilling and dallying with a freaking air pump, make sure to leave a like and subscribe. It helps me out a ton, and it also lets me know that you guys would be interested in a future video on actually making the pump and actually making the rocket and actually making the rocket go up. So make sure to leave a like and subscribe if you guys want to see that. Thanks for watching.